This video is on how to solve optimization problems. By the end of this lesson, you should be able to solve optimization problems, including polynomials, simple rational, and exponential functions drawn from a variety of applications, including those arising from real-world situations. So the idea of optimization is to mathematically determine the values of variables within a problem that produce the best possible outcome, either by minimizing or maximizing. Often this is called min-maxing. There are typically a set of restrictions on the variables that also must be observed. So you might recall from past grades, we've had questions where you have to find the maximum area for a rectangular garden, given that you have, say for example, 250 meters of fencing, and one side of the garden is up against a wall. Determine what is the best possible dimensions to create a maximum area. If you have some ticket sales, you can maximize the revenue given data about the number sold based on the ticket price. Also maximizing the volume of an open top box made from a sheet of cardboard with given dimensions. So these were all problems that you may have encountered in both grade 10 or grade 11. And now we're going to use calculus to be able to solve these. So the first thing that you have to do is you have to read and try to understand the problem. Then once you've done reading the problem, identify the variables involved. Okay. Draw and label a diagram when possible. Determine a function that represents the quantity to be optimized. The function should only depend on one variable. So we're going to have something that is dependent on something else. You have a dependent variable and an independent variable. There may be another equation that can be created to substitute into the main function, so that is based on one variable. The next thing that we're going to do is that we are going to determine the domain of the function in the context of the problem. So like, what are the allowable values for the independent variable? And then we're going to find the extreme values as we did in our last lesson. So recall, you find the first derivative, set it equal to 0. That will give your relative extrema. And then you find the function at those extrema and then also compare it to the endpoints. So just to quickly go back to what we did before, let me show you this. Okay. So what we did is we found the min, the max, and then we also compared the value of the functions at the endpoints as well. Okay. So we're going to do the same thing, except this has to do with word problems. And we're going to jump in right away with a word problem here. And we're going to start with a revenue problem, which is a problem that you saw back in grade 10 and possibly again in grade 11. So I'll read out the problem right now. A commuter train carries 2,000 passengers daily from a suburb into a large city. The cost to ride the train is $7 per person, and market research shows that 40 fewer people would ride the train for every 10 cent or $0.1 increase in the fare. If the capacity of the train is 2,600 passengers, and carrying fewer than 1,600 passengers means that costs exceed revenue, what fare should the railway charge to maximize revenue? So what I'm going to do is I'm going to set up a variable here. And it looks like I'm increasing the fare in 10-cent increments. So I'm going to write over here, and this is typically how we approach these revenue problems. Let x represent the number of 10-cent increases in fare. Okay. Then you will have a revenue function. Revenue as a function of x represents the revenue as a function of the number of 10-cent fare increases. Okay. So recall that revenue is defined as follows, or the revenue function is defined as follows. Revenue is equal to the selling price multiplied by the number sold. Okay, let's go back to the original question here. Let's take a look at the selling price. The cost to ride the train is $7. So what I'm going to do is I'm going to set up my revenue function, revenue as a function of those fare increases. So I'm starting with $7. The cost to ride the train is $7 per person. And we're increasing it each time by 10 cents. So every time we increase the fare, it is by 10 cents. So every time we increase it, we are increasing the fare by 10 cents. Okay, so we're starting off with $7 and increasing it by 10 cents every time. The number sold, okay, so looks like we are starting off, our baseline is we have 2,000 passengers riding. But then every time we have a fare increase, 40 fewer people ride the train. So that means 40 fewer every time we increase the fare by 10 cents. So as you can see here, my selling price is given. It's multiplied by the number of sold. And perhaps for those of you that are looking at this and looking at the distributive property, you can see that this is going to yield a quadratic. And recall that a quadratic has either a min or a max, which is, again, what we are looking at in this unit, min-maxing, okay? Now, the other thing that we have to look at we have to look at our constraints, okay? And so we have to look at our domain. So I'm just going to do a little side note here in green, and I'm going to look at our domain. So you might be thinking, okay, well, what do you mean by domain? Well, let's see. What are we constrained by? Well, it looks like the capacity of the train is 2,600 passengers, and I can't carry fewer than 1,600 because then cost will exceed the revenue. So that's going to put a restriction on how much I can change the price. So let's look at this 2,600. If I reduce the price too much, then the number of passengers riding will exceed the capacity. So that's a constraint on the domain. If I reduce the selling price too much, I'll have too many people riding. If I raise the price too much, too few people will ride, and then my cost will exceed the revenue. So let's start with looking at capacity. Okay, so let's just look at my maximum capacity. So let's look at the maximum capacity situation. What is my restriction on that domain? Well, the number of sold, so 2,000 minus 40x would be equal to 2,600 if I am at capacity. So what I'm going to do here is I'm just going to isolate x. Okay. Okay. And as you can see right here, I end up with a negative x value. Well, how could we have negative increases in fare? Well, I think you can probably work it out. A negative increase in fare just means a decrease in fare. So if we decrease the fare 15 times at 10-cent increments, okay, then the train is going to reach its capacity. Does that mean that it's going to have a maximum revenue? Well, not necessarily. We may have more people riding, but we're also selling at a lower price. Okay, so let's look at our minimum capacity situation. Okay, so our minimum capacity situation is we're going to again look at the number sold. So we have 2,000 minus 40x, and that's going to be equal to, I believe it was 1,600. Okay, so then I go and I isolate for x. Okay, and I'm going to skip some steps here because I know you guys know how to isolate this. And I get x is equal to 10. All right, so that means if I raise the price 10 times at 10-cent increments each, then I am going to have the minimum number of people riding, right? I'm going to have a high selling price, but I won't have as many people riding, all right? And this is basically the highest I can go in terms of my number of increments, and this is the lowest I can go in terms of my number of increments. So as you may recall from the previous lesson, okay, I'm going to have this right here. This is going to be my constraint on the domain, okay? So x has to be a number between -15 and 10. Okay, now what I'm going to do is I'm actually going to get to the calculus portion, and I genuinely think this part of the question is probably the more challenging aspect of it, in that you have to really think about taking the context of the question and finding out the restrictions on the domain. The rest of it becomes, well, fairly algebraical, if that is even a word. Okay, so I'm going to go ahead and I'm going to go and expand this out. Okay, so expanding this out is going to yield 14,000 minus 280x plus 200x, and then minus 4x squared. Okay, great. I'm going to rearrange that so that we can see it in a form that we're a little bit more familiar with and collect my like terms. Okay, so here we go. So as you can see, the revenue function is in fact parabolic, and it's parabolic opening down. So I will have a maximum revenue, right? Revenue will be at a maximum point since it's a parabolic function opening down, and the x value is where I can maximize my revenue, right? So what we can do is we can use our calculus and we can find the first derivative, right? That'll help us find our critical point. So we get -8x minus 80 right here. Okay, and so recall that in order to find the extrema, you set the derivative equal to 0. So 0 is equal to -8x minus 80, and I think you can piece it together. Therefore, x is equal to -10. Okay, so what I need to do now is I need to check if this falls within my domain. Okay, does -10 fall within the constraints that I placed on the domain? Looks like it does. So what I'm going to do is I'm going to check if this maximum produces the maximum revenue, and then I'm also going to look at the endpoints as well of the domain. Okay. But if you think about it right here, right, this will in fact have to produce the maximum, right? Because if this is the highest point on the revenue function. But for the purposes of being thorough, okay, I am going to actually evaluate the revenue at -10 increases, the revenue at -15 increases, and the revenue at 10 increases. Okay, so let's start right here and let's actually evaluate this at -10. Okay, so if I evaluate this at -10, I plug -10 into the original equation and I get $14,400. So that's my revenue if I decrease the fare 10 times at 10-cent increments. So that means that I'm decreasing the fare to $6. Okay, that's stunning mental math right there. Okay, now if I have 10 increments, then again I'm raising the price by $1, and so I'll sub 10 into my revenue function. Okay, and I get $12,800, right? Okay, so we can already see where this is going, and let's check my other endpoint. So, okay, if I decrease the fare by $1.50, that is to say, if I decrease the fare 15 times, each time at 10 cents, Okay, so then I will end up with 14,300. Okay, so this is my winner right here. So I'm going to say therefore, okay, the maximum revenue, the max revenue happens when X is equal to negative 10. So again, I'm not increasing the fare 10 times because there's a negative value there. I'm going to decrease it, right? So I'm decreasing the fare 10 times. So therefore, my fare, okay, which was my selling price, is equal to $7 plus, again, 10-cent increments. Okay, so therefore, the optimal fare is $6. All right, so just quickly to review, I set up the revenue function. 1 second, just click here. Okay, set up my revenue function. I recognized, and you can tell by the language of it, right, what you're going to let X represent. It's the number of 10-cent increase in fares. Okay, do my selling price number sold, look at my restrictions on the domain. Okay, then get my revenue function, so expand it out, take the first derivative, set it equal to 0, find that critical number, sub the critical number in, and then compare it with the endpoints of the domain, and then find out what your extreme value was, okay? And so, or your best value, your optimized value. Okay, so we min-maxed here and we got a fare of $6. The next thing that we're going to look at right here is a problem in which we have a cylindrical chemical storage tank with a capacity of 1,000 meters cubed, and it's going to be constructed in a warehouse that is 12 meters by 15 meters with a height of 11 meters. The specifications call for the base to be made of sheet steel that costs $100 per meter squared. The top, okay, is going to be made by sheet steel that costs $50 per meter squared, and the wall has to be made up of sheet steel that costs $80 per meter squared, so the wall right here, okay? So you can see here that we're dealing with simultaneously a volume problem because we know that the volume has to equal to 100 meters cubed. Okay. We also know that the dimensions have to fit in this warehouse. Okay, so that's something that you need to be actively thinking about. Okay, I know that my volume has to be 1,000 meters cubed. You also need to recognize, well, I can't have a radius that's going to go beyond the constraints of the warehouse, right? A radius that when doubled goes beyond the constraints of the warehouse, or worse, right? Or not worse, I mean equally as bad. If the height is beyond 11 meters, it's not going to fit in the warehouse, right? So you can already start to see the constraints on your domain. And then what we are going to try to do is we are trying to minimize the cost of steel. So we're going to look at the surface area of the top, the surface area of the bottom, and the surface area of the side, right there, okay? And then when we multiply it by its cost multiplier, we're going to try to minimize that cost, okay? All right, so let's take a look right here and answer this question. Determine the restrictions on the radius and height of the storage tank. So I think probably the easiest one to see right away is the height has to be obviously greater than 0, but it has to be less than 11. Okay, so let's start with that. Okay, so the height has to be greater than 0, but less than 11. Okay, and then if we think about this right here, it has to be constructed in a warehouse that is 12 meters by 15 meters. Okay, so this is my height restriction. Let's look at the radius. Well, if the footprint or the base of the warehouse, okay, is 12 by 15, and my cylinder has to be in the middle here, right? That means that my radius can be no larger than 6 meters, right? Otherwise, it's going to exceed the walls of the warehouse. So there's kind of a little rough diagram for you to help you understand what the restrictions are on the radius. Okay, so my radius has to be between 0 and 6. All right, now take a look here. We have two variables. We have radius and we have height. So we have to find, okay, well, I can't have cost, radius, and height. What I need is cost to be dependent, right? Cost is my dependent variable. I need cost to be dependent on one of these variables. And so what I'm going to have is I'm going to have the cost be dependent on radius. And I can get an expression for height in terms of radius by looking at the volume. I know that volume has to be 1,000 meters cubed. I also know that volume of a cylinder is given as pi r squared times h. And if you think about that right there, the volume of a cylinder is the surface area multiplied by the height. Okay, the surface area of the cylinder multiplied by the height. That's the volume of your cylinder. So if I know that volume is 1,000 meters cubed, I can write 1,000 meters cubed is equal to pi r squared h, right? And then I can isolate h right here. I'm just going to isolate h. I'm going to write 1,000 over pi r squared is equal to h. Now, whenever I have h in my cost function, I'm just going to replace it or substitute it with this expression right here. So 1,000 over pi r squared. Okay, so my cost function, all right, is going to be, is a function of, all right, so the surface area of the top, surface area of the bottom. So let's actually write that out, okay? So cost, right, is going to be equal to surface area of top times cost of the top plus surface area of the bottom times the cost of the bottom, right? Plus surface area of the side times the cost of the side. Okay, so what we're going to do right here is we're going to look at cost, and I'm going to look at cost as a function of radius because I'm not going to deal with height. I can actually have height in terms of radius. So cost as a function of radius. Well, the surface area of the top is just equal to pi r squared, and the cost of the top is going to be 50 meters, or $50 per meter squared. So times 50. Okay. Then I'm going to look at the surface area of the bottom. Well, it's the same thing. It's pi r squared. But what's different is the cost of the bottom is $100 per meter squared. Then I think the tricky thing to the surface area of the side is basically like a rectangle. And you've got the height of a rectangle, and then you've got the length of the rectangle. But the length of the rectangle is actually just the circumference of the cylinder, right? So if we were to peel the side, it's one long rectangle that's curved around on itself, and the length of the rectangle, so the length of the rectangle is just 2 pi r, which is the circumference. So the surface area of the side of a cylinder is given as 2 pi r. And then the cost of that side is, I believe, $80. Okay, so we have cost as a function of radius here, okay? And I'm going to collect some like terms right here. These ones right here can be added together. So we've got 150 pi r squared, right? One thing that I forgot right here is 2 pi r is just the length. I need to multiply by h right there, okay? Plus 2 pi r h times 80, okay? But what I need to do is I need to sub h is equal to 1,000 over pi r squared. So, all right, here we go. 2 pi r, and instead of h, I'm going to write 1,000 over pi r squared. multiply that by 80. Okay, let's cancel out some things that we can cancel in the second term here. Okay, looks like I can cancel my pi. I can also cancel an r. Okay, and then I end up with this final function. Okay, so I get 150 pi r squared. Okay, and then I multiply all this together, and I get 160,000. And I have one r in the denominator, so I'm just going to actually write r to the negative 1 right there. Okay, so note that I can evaluate the radius at the extremes. Okay, obviously I'm not going to evaluate it at 0, right? But I can also try and find an extrema in between 0 and 6. See if an extrema exists between 0 and 6. So I'm going to take the first derivative. Okay. And when I take the first derivative, I get 300 pi r minus 160,000, right, times r to the negative 2. Okay. And you may recall from the last unit that if I want to factor this out, I usually try and factor out the r to the most negative, or the variable to the most negative value, or the lowest value. So I'm going to factor out an r to the negative 2. Okay. I'm also going to factor out a 100. And I end up with 3 pi r cubed minus 1,600. Okay. So obviously radius can't equal to 0, so I can write radius does not equal to 0 for contextual reasons, as well as creating an undefined expression here. So the only critical point I'm going to look at is when this is equal to 0. Okay. And so I'm going to rearrange and solve. So I've got 1,600 all divided by 3 pi, and then I'll take the cube root of that to get my r value. Okay. And I get an r value that is approximately equal to 5.54. And just as we did in the previous question, I'm going to check to see that 5.54 is within my restricted values. It certainly is. Okay, so it's within the domain. So now what I'm going to do is I'm going to look at this value right here. Okay, I'm going to look at the extreme of 6. Okay, and then I'm also going to look at 5.54. Okay, so let's look at those extremes, right? In C, so I'm looking at the cost if my radius was 6. And so what that means in the context of this problem is if the radius is in fact equal to 6, and I can change this right here, right? If it is in fact equal to 6, that means that this is really just built right up against the side of the wall here. Okay, it's like it's touching the side of the warehouse wall. So let's evaluate it right at that extreme right there, 6. Okay. So if I look at the cost at 6, okay, that's going to be equal to 150 pi 6 squared plus 160,000 all divided by 6. Okay. And then the cost if my radius was 6 is equal to $43,461.27. Now I can look at the cost at this radius right here, 5.54. And when I insert that in, the cost at that radius is $43,343.94. Okay. So therefore, the cost is lower when R is equal to 5.54 meters. And so I'm going to take this value and then I'm going to find the height. Height is equal to 1,000 over pi 5.54. I'm going to square that. And so the height is equal to 10.37. I check, yep, that definitely works within the confines of my dimensions, okay? And in order to minimize the cost of the materials, so I'll say, therefore, to minimize cost, radius should be 5.54 meters and height should be 10.37 meters. Okay, going back up here, took a look at the constraints on the domains, okay, of both height and r, but then using radius, using expression for radius, I was able to definitely get a cost function, and I used the volume constraint of 1,000 meters cubed to find an expression for h. Sub that back in, found a cost function as a function of radius, found the first derivative, and then found the extrema, and also compared with the outer end, or the most maximum radius possible, compared the two costs, and it is cheaper to make the radius 5.54 meters. Okay, thank you very much for watching.